Hello students, welcome to Educate. Today we are going to start the next chapter of class 12 physics. The chapter is dual nature of radiation and matter. So let's see the basics. Here dual nature means wave nature and particle nature. If you remember, charge on electron is 1.602 into 10 power minus 19 coulomb, and this fact was established by Millikan's oil drop experiment, in which he determined the value of E upon m. Later on we will see about it. Now here we are going to see electron emission. Electron emission means emission of electron from metal surface when light of suitable frequency strikes on it. So different type of electronic emission are there, but before that we must know what is work function of metal. Means minimum energy required to eject the electrons from its surface, that is called work function. It is denoted by phi 0 and measured in electron volt. Now question arises, what is electron volt? So electron volt is unit of energy. It is the energy acquired by an electron when accelerated through 1 volt potential difference. So you can say that 1 electron volt is equal to 1.602 into 10 power minus 19 joule, means 1 electronic charge times 1 volt. Now, this unit of energy is commonly used in atomic and nuclear physics. The work function phi 0 depends on the properties of the metal and the nature of its surface. Minimum energy required for the electron emission from the metal surface can be supplied to the free electrons by any one of the following physical processes. So, we are going to see one by one. Number one, thermionic emission means giving sufficient temperature. So when a material is heated sufficiently, then electrons gain energy and then they come out. Second type of emission is field emission. It means electric field is applied, and due to that strong field, electrons will experience a force and hence they will be pulled out from the metal surface. Here the value of voltage or electric field is 10 power 8 volt per meter, which is typical value. Then comes photoelectric emission. Photoelectric emission means when light of suitable frequency falls on the metal surface. In that case, electrons are emitted and such electrons are called photoelectrons. In this chapter, we will study the properties of photoelectrons and related facts. So let's see what is photoelectric effect. So photoelectric effect means same thing, that light falls and the electrons gain certain energy, and when this energy is more than the threshold energy, in that case electrons will gain certain kinetic energy and they will come out. So let's read this. Hertz observation. The phenomena of photoelectric emission was discovered in 1887 by Heinrich Hertz during his electromagnetic wave experiments. In his experimental investigation on the production of electromagnetic waves by means of spark discharge, Hertz observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Light shining on the metal surface somehow facilitated the escape of free charged particles, which we now know as electrons. When light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of the positive ions in the material of the surface. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding space. Now, Hallwards and Lenard's observation. Wilhelm Hallwards and Philip Lenard investigated the phenomena of photoelectric emission in detailed during 1886 to 1902. Leonard observed that when ultraviolet radiations were allowed to fall on the emitter plate of an evacuated glass tube enclosing two electrodes, we will see this picture, metal plates, current flows in the circuit. As soon as the ultraviolet radiations were stopped, the current flow also stopped. These observations indicate that when ultraviolet radiations fall on the emitter plate C, electrons are ejected from it, which are attracted towards the positive collector plate A by the electric field. The electrons flow through the evacuated glass tube, resulting in current flow. Thus, light falling on the surface of the emitter causes current in the external circuit. Halvatz and Leonard studied how this photoelectric current varied with the collector plate potential and with frequency and intensity of incident light. So graphically we will study these things. Then Halvatz in 1888 undertook the study further and connected a negatively charged zinc plate to an electroscope. He observed that the zinc plate lost its charge when it was illuminated by ultraviolet light. Further, the uncharged zinc plate became positively charged when it was irradiated by ultraviolet light. Positive charge on a positively charged zinc plate was found to be further enhanced when it was illuminated by ultraviolet light. From these observations, he concluded that negatively charged particles were emitted from the zinc plate under the action of ultraviolet light. After the discovery of the electron in 1897, it became evident that the incident light causes electrons to be emitted from the emitter plate. Due to negative charge, the emitted electrons are pushed towards the collector plate by the electric field. Halvatz and Leonard also observed that when ultraviolet light fell on the emitter plate, no electrons were emitted at all when the frequency of the incident light was smaller than a certain minimum value. This is called threshold frequency. So this is obvious. If frequency will be less than this threshold frequency, in that case, no photoelectric emission will occur. This minimum frequency depends on the nature of the material of the emitter plate, right? So for different material, this threshold frequency will have different values. It was found that certain metals like zinc, calcium, magnesium, etc. responded only to ultraviolet light, having short wavelength to cause electron emission from the surface. However, some alkali metals such as lithium, sodium, potassium, cesium and rubidium were sensitive even to visible light. All these photosensitive substances emit electrons when they are illuminated by light. After the discovery of electrons, these electrons were termed as photoelectrons. The phenomena is called a photoelectric effect. So this is basic. Now experimental study of photoelectric effect. So here, if you observe the diagram, light is falling, then electrons are emitted, then there is here current flows, so that all is controlled by this. This is rheostat variable resistor. Here certain voltage is applied to make this positive, right? So this picture you can observe. So let's describe it. Description we can read. It consists of an evacuated glass quartz tube having a thin photosensitive plate C. This is photosensitive plate C, and another metal plate A. This is metal plate A. Now, monochromatic light from the source S of sufficiently short wavelength. So this is source from where monochromatic light is falling on this plate through this quartz window and falls on the photosensitive plate C. This plate is also called emitter because it emits electrons. A transparent quartz window is sealed onto the glass tube, which permits ultraviolet radiation to pass through it. So ultraviolet radiations are coming through it, and then which permits ultraviolet radiation to pass through it, and it radiates the photosensitive plate C. The electrons are emitted by the plate C. From here, electrons are emitted and are collected by the plate A. So plate A is called collector because electrons are collected by the electric field created by the battery. Here, electric field is created by the battery, right? So here battery is given. This is rheostat, you know. Now, the battery maintains the potential difference between the plates C and A that can be varied. The polarity of the plates C and A can be reversed by commutator. Here commutator is used. If we wish, we can change the polarity. Here it is positive. Now if we wish, we can make it negative. In that case, what will happen? If it becomes negative, then these electrons will stop, right? So that also we have to check. So what is the maximum value? And that will be used to determine the kinetic energy of these electrons, right? The polarity of the plates C and A can be reversed by commutator. Thus, plate A can be maintained at desired positive or negative potential with respect to emitter C. When the collector plate is positive with respect to the emitter plate, if this is positive, then electron will move, right? The electrons are attracted to it. The emission of electrons causes flow of electric current in the circuit. The potential difference between the emitter and collector plates is measured by voltmeter. Here this voltmeter is applied, and whereas the resulting photoelectric current will be measured by the micrometer. Here there is micrometer. Current will be very less. That is why micrometer is used. The photoelectric current can be increased or decreased by varying the potential of the collector plate A. So by varying the potential of this, photoelectric current can be increased or decreased. The intensity and frequency of the incident light can be varied, as can the potential difference be between the emitter C and collector A. Now we can use the experimental arrangement to study the variation of photoelectric current with the intensity of radiation. So first thing we will see graphically that how does photoelectric current vary with the intensity of radiation, then with frequency, and then potential difference between the plates A and C, and the nature of the material of the plate C. So these all things we are going to study. Light of different frequencies can be used by putting appropriate colored filter or colored glass in the path of the light falling on the emitter C. The intensity of light is varied by changing the distance of the light source from the emitter. So here first graph is observed photoelectric current and intensity of light. Both are proportional. It means if intensity of light is increased, then photoelectric current will increase. Same thing is given here. So this implies that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. Keep this in mind. Number of photoelectrons depend on the intensity of incident radiation. Then comes effect of potential on photoelectric current. So here stopping potential. Stopping potential means potential applied to stop the electrons. So even if intensity is different, in every case you are observing that here intensity is less, then stopping potential is V0, it is negative, and if intensity is more, still stopping potential is same. Here also intensity is being increased, but stopping potential is same. It means whatever may be the intensity, the total kinetic energy possessed by photoelectrons will be same, right? So this thing you can read, and here the potential applied to stop the electron is called either retarding potential or stopping potential, right? So here retarding potential means potential applied to stop the electrons, to slow down the electrons, and finally a value is arrived where all electrons stop moving. So that is called stopping potential. So this graph you have to remember that photocurrent, this is photocurrent and this is intensity. So higher intensity means more photocurrent, but as far as energy is concerned, so they will possess same energy. That is why their stopping potential is same, right? Now further, here we can determine on the basis of stopping potential what will be the maximum kinetic energy possessed by these photoelectrons. So K max will be equal to electronic charge times stopping potential, right? So we will make use this expression for calculating the kinetic energy of electron. So here for a given frequency of the incident radiation, the stopping potential is independent of its intensity, right? You have seen three cases when intensities were more. Still in all three cases what we have observed that stopping potential remain same, right? Now we are going to see the effect of frequency. Here what do you observe? Nu 1 stopping potential is for nu 2 frequency is increased, then stopping potential is increased, and nu 3 stopping potential is more. It means if frequency is more, in that case stopping potential will be more. What does this imply? This implies that frequency is directly proportional to energy. Means if frequency is more, energy will be more. So more stopping potential will be needed. So this is clear from the diagram, you can read it. Then comes here the graph is plotted between frequency of incident radiation and the stopping potential. What do you observe? So here metal A, metal B. So in case of metal A, this is threshold frequency nu 0. For metal B, threshold frequency is more. So this graph is very clear. Stopping potential will also vary further too. If you go for this, here frequency is less, so its stopping potential will be less. Here if you extend it up to extrapolate it, so you will find stopping potential corresponding to metal B, and that will be larger. Right. So here the same thing is shown. The stopping potential V0 varies linearly with the frequency of incident radiation for a given photosystem material. There exists a certain minimum cutoff frequency U0 for which stopping potential is 0. So these are those values where stopping potential is 0. Alright. Now, so these observations have two implications. Number one, the maximum kinetic energy of the photoelectrons varies linearly with the frequency of incident radiation, but is independent of its intensity. Number two, for a frequency nu of incident radiation lower than the cutoff frequency nu 0, no photoelectric emission is possible even if the intensity is large. So this minimum cutoff frequency nu 0 is called the threshold frequency. So you have understood, if frequency is less than this value for particular metal, then no photoelectric emission will be observed. Different metals have different threshold frequencies. So different photosensitive materials respond differently to light. Selenium is more sensitive than zinc or copper. The same photosensitive substance gives a different response to light of different wavelengths. For example, ultraviolet light gives rise to photoelectric effect in copper, while green and red light does not. Right? So these points you have to keep in mind. Note that all the above experiments, it is found that if frequency of the incident radiation exceeds the threshold frequency, the photoelectric emission starts instantaneously without any apparent time lag, even if the incident radiation is very dim. It is now known that emission starts in a time of the order of 10 power minus 9 seconds or less. So let's see the result. We can summarize these points. You have to memorize. They are very important. For a given photosensitive material and frequency of incident radiation above the threshold frequency, the photoelectric current is directly proportional to the intensity of incident light. This is the first point. Second point, for a given photosensitive material and frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas the stopping potential is independent of intensity. Stopping potential depends on frequency. Then for a given photosensitive material, there exists a certain minimum cutoff frequency of the incident radiation called the threshold frequency, below which no emission of photoelectrons take place, no matter how intense the incident light is. Above the threshold frequency, the stopping potential are equivalently the maximum kinetic energy of the emitted photoelectrons increase linearly with the frequency of the incident radiation, but is independent of its intensity. And the last point is the time lag. The photoelectric emission is an instantaneous process without any apparent time lag, roughly 10 power minus 9 seconds, which is very less, even when the incident radiation is made exceedingly dim. So it does not matter whether they are dim or bright, but time lag will be less than this, or roughly equal to 10 power minus 9 seconds. 10 power minus 9 seconds means it is instantaneous process. Now, photoelectric effect and wave theory. So here we will see certain. According to the wave picture of the light, the free electrons at the surface of metal over which the beam of radiation falls absorb the radiant energy continuously. The greater the intensity of radiation, the greater are the amplitude of electric and magnetic fields. It seems to be so, but it is not the case. Consequently, the greater the intensity, the greater should be the energy absorbed by each electron. In this picture, the maximum kinetic energy of the photoelectrons on the surface is then expected to increase with increasing intensity. Keep in mind, this is wrong concept. Also, no matter what the frequency of radiation is, a sufficiently intense beam of radiation over sufficient time should be able to impart energy to the electrons so that they exceed the minimum energy needed to escape from the metal surface. A threshold frequency therefore should not exist. So this is wave picture, but that is not correct. And further, we should note that in the wave picture, the absorption of energy by electron takes place continuously over the entire wavefront of the radiation. Since a large number of electrons absorb energy, the energy absorbed per electron per unit time turns out to be small. Explicit calculations estimate that it can take hours or more for a single electron to pick up sufficient energy to overcome the work function and come out of the metal. Here, there must be time lag according to this concept, but as we have observed that time lag is very, very small as 10 power minus 9 second. This conclusion is again in a striking contrast to variations that the photoelectric emission is instantaneous. In short, the wave picture is unable to explain the most basic features of the photoelectric emission. So this question is generally asked that wave picture can't explain the photoelectric effect. Why? So reason is obvious. You have to find out. There are 3 points. Now, we are going to see Einstein photoelectric equation, energy, quantum or radiation. So what is Einstein photoelectric equation? In this equation, we are going to study that when certain radiations of frequency nu strike on the metal surface, then certain amount of energy will be used as work function and remaining energy will provide the kinetic energy to the photoelectrons. So we can say this is total energy of incident radiations and phi 0 is the work function. So after doing the difference of the two, whatever energy is left, that will be kinetic energy of the electrons. Alright, and if K max is 0, it means the energy of incidental radiations is same as the work function of the metal or less than that, right? So this is basic equation, and the energy packets we study quanta, that is equal to h nu. So in terms of h nu, each photon has energy h nu, all right? So we have seen this thing like K max means total kinetic energy, maximum kinetic energy depends linearly on frequency and is independent of intensity of radiation. In agreement with the observation. This has happened because in Einstein picture, photoelectric effect arises from the absorption of the single quantum of radiation by a single electron. The intensity of radiation that is proportional to the number of energy quantum per unit area per unit time is irrelevant to this basic process. So K max must be non-negative, of course. So if it is non-negative, it means energy of incident radiations must be greater than the work function in that case, or this is frequency of incident radiation, this is threshold frequency, that must be larger. So here nu must be larger than nu 0, otherwise photoelectric emission will not occur, and hence we can say nu 0 is equal to phi 0 divided by h. So these are the basic things that you have studied. I'm not going in detail here. You can read it out, and let's see further. The same equation is written here. The kinetic energy, as we have studied, that EV0 is h nu minus phi 0. Phi 0 is work function. Or from here, we can see that V0 can be written as h upon E times nu minus phi 0 upon E. This is, does it remind you of something? Y equal to mx plus c. So here m will be h upon E, slope. This slope is, this is stopping potential, this is frequency. So graph is plotted between stopping potential and frequency, and this is of this form. Here this is intercept that will come on the negative side. So phi 0 upon E. Alright. So slope from here, if you are given this type of equation, then h upon E will be the slope, and from there you can determine the value of Planck constant. So now, if you remember, value of Planck constant is 6.63 into 10 power minus 34 joule second. So these things are basics that you have understood. Particle nature of light, the photon picture. So light is made up of small packets. They are called photon, having energy h nu, and then we can convert it h nu upon c. Also here momentum, if we want to find out of photon, then we can say h nu upon c, and after that we can summarize the photon picture of electromagnetic radiation. In interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. Each photon has energy equal to h nu and momentum p equal to h nu upon c, and the speed c, the speed of light. All photons of light of a particular frequency nu or wavelength lambda have the same energy equal to h nu or hc upon lambda, and momentum h nu upon c or h upon lambda, whatever the intensity of radiation may be. By increasing the intensity of light of given wavelength, there is only an increase in the number of photoelectrons per second crossing a given area, which with each photon having the same energy. Thus, photon energy is independent of intensity of radiation. Photons are electrically neutral and are not deflected by electric and magnetic field. In a photon particle collision, such as photon electron collision, the total energy and total momentum are conserved. However, the number of photons may not be conserved in a collision. The photon may be absorbed or a new photon may be created. So, in this video, this is all. We will study other things in next video. Thank you for watching. Team Educate.